Hi, I'm Mark Morris. I'm an environmental engineer with the United States Environmental Protection Agency. In this module, we'll demonstrate the human exposure model of the risk assessment course. In other modules, you learned about the fate and transport of air pollutants and also about human exposure and risk. One tool you can use to estimate human exposures and risks from the inhalation of hazardous air pollutants is the human exposure model, or HIM. This presentation is an introduction to the current version of HIM, called HIM3. We'll use the terms HIM and HIM3 interchangeably. This presentation will be followed by a demonstration of the model. The main purpose of HIM is to estimate inhalation exposures and risks to people over the long term, so the receptor locations of interest are people's homes. Because nationwide residence data are not practical to use, HIM uses the approximately 6 million census block centroids as surrogates for residences. People are assumed to be at these locations 24 hours a day, 7 days a week for 70 years. This is sometimes called the porch potato exposure scenario, and is conservative, or upper end, because most people will not be exposed that long. HIM does not account for people going to work, school, or other locations and being exposed at different levels in those microenvironments. And HIM is a simple exposure model in this respect. HIM uses the air mod dispersion model to estimate pollutant concentrations at two types of receptors. The first receptor type is the census block centroid already discussed for long-term exposures. The second receptor type is the polar receptor, which is a grid point on a set of rings and radials originating at the sources. These are used to represent locations of short-term exposures where people may be for an hour or up to a day. With concentration estimates from AirMod and with pollutant health reference values, HIM estimates various risk metrics. We should note that HIM also accepts concentration data from previous model runs, in which case the AirMod step is bypassed. This picture is an example of the census block receptors near a facility. The blocks are shown as green X's, and the emission sources are shown as red X's or polygons, depending on whether they are point or area sources, near the center of the image. Notice that there are no receptors located in the industrial areas. This is because people do not live there, and we don't want to estimate long-term human exposures there. You may also notice that there are no receptors shown beyond a certain radius, even though there are residential locations there. This is because running all the census blocks within 50 kilometers of a facility explicitly in AirMod would significantly increase run times. So only the nearby blocks are modeled explicitly to capture where the maximum exposures are likely to occur. Estimates for the more distant census blocks are interpolated from the polar receptor grid, which is a much smaller data set. You can see that the polar receptors are made of a set of concentric circles or rings and outward radials. Near the facility, these receptors are used to estimate short-term exposures, for example, at the facility fence line. You may also notice that the polar receptors extend out to the full modeling domain, and the more distant polar receptors are used to interpolate values for the more distant census blocks. This is an overview of HIM. The model and its supporting data are available at EPA's Fate Exposure and Risk Assessment, or FARA, webpage. HIM performs three main operations, including dispersion modeling, estimating maximum health risks, and estimating population risks, such as cancer incidence and the numbers of people within specific risk or hazard ranges. Key features of HIM include the ability to model facilities with complex configurations and multiple source types, like point, area, polygon, and volume sources. Most of the AirMod model options are also available in HIM, including modeling terrain, where receptor elevations are substantially different from source elevations, estimating particle and vapor deposition and plume depletion, accounting for building wake effects, where nearby buildings may affect plume dispersion, and time-varying emissions, such as by hour of the day of the week, seasonally, and so on. A natural question to ask is, why use HIM? Why not just run AirMod by itself? There are several answers to this question. First, running AirMod by itself for a few facilities is feasible, but you may need to do dispersion modeling for many facilities, sometimes hundreds or even thousands, with multiple emission sources at each facility and with multiple pollutants from each emission source. AirMod is a single pollutant model, so HIM does a lot of the accounting for you. We're also interested in specific receptors for human exposures, the census block centroids, and this dataset is built into HIM. Aside from the exposure concentration supplied by AirMod, HIM provides much more information about risks, including maximum individual cancer risk, or MIR, cancer incidence, maximum non-cancer hazards, population risks, and other information. Because the AirMod model is such an integral part of HIM, it's important to discuss the multiple preprocessors that need to be run before an AirMod run can be done. The preprocessors that would need to be run depend on what modeling options are chosen. AirMod needs meteorology data, and the air surface and AirMet preprocessors are used for this. AirMet processes hourly data like wind speed, wind direction, and mixing height. Characteristics of the ground surface can affect dispersion, and there are 3 surface characteristics processed using the air surface program, the most important one being surface roughness, which is related to the height of surface elements like trees, grasses, man-made structures, and so on. HIM has a built-in library of over 800 MET stations with 2011 data processed with air surface and AirMet. These data are used by default if a user does not specify their own MET data. Because receptor elevations relative to emission source base elevations can affect predicted concentrations, AirMod needs to know the elevation of all receptors, and AirMap does this. HIM has a receptor library that includes all 6.2 million census block centroids, and this library already includes the elevation of these blocks. If the terrain around a facility is mostly flat, AirMap may not need to be run. Finally, structures near emission sources can affect dispersion. This is called building downwash. And the Building Profile Input Program, or BPIP, calculates relevant parameters used in AirMod to take the nearby structures into account. These parameters include building heights, widths, and other values. This information is very site-specific, so there are no built-in databases for this. The HIM model accepts the outputs of BPIP or, alternatively, the same information from an existing AirMod input file. As with all models, there are limitations to HIM. First, HIM is an inhalation model only. It is designed only for the air pathway and the inhalation route of exposure, so it cannot be used to estimate exposure through ingestion or dermal routes. HIM is a simple exposure model in that it doesn't account for the movement of people away from their home census blocks and does not account for possible lower indoor versus outdoor pollutant concentrations. Finally, census block centroids may not always be a good surrogate for people's homes. There can be cases where someone's home may be closer to a facility than the block centroid, so their exposure and risk would be higher than that estimated by HIM at the centroid. This limitation can be remedied by including additional receptors, which is allowed in HIM, on a case-by-case basis to account for other potential exposure locations. This figure shows the flow of the HIM model. Starting with input data, HIM needs, at a minimum, data on emission sources. This includes the amount of annual emissions, the accurate location of the sources, and release parameters such as emission release height, exit velocity, and temperature. There are other optional inputs needed depending on whether you want to account for building downwash, variable emission rates, and deposition and depletion. After receiving inputs, HIM creates an AirMod input or run stream file and then runs AirMod. The outputs of AirMod are the short-term and long-term concentration estimates at all receptors of interest. With these concentrations and pollutant dose response values, HIM estimates cancer risk and non-cancer hazards at the receptors. Using the population data from the census data set, HIM also estimates cancer incidence and population risks, which are basically the numbers of people at specific risk levels. With this introduction, we're now ready to go through a demonstration of HIM. To start the HIM model, you can go to wherever you installed HIM In this case, it's on the C drive under the HEM3 directory. And find the HEM3 executable. You may have added this to your desktop also, but here we will just execute it from this directory. The first screen that HEM shows you is just a reminder for you to check your dose response library. This is the files that have your hazardous air pollutant data in them, cancer unit risk values, and that kind of information. This is just a reminder to let you know that you need to keep those up to date. This first screen specifies basic model run information. The first piece of information is the name of your output file, where you want all your output files to go. Since we are doing a demo here of Big Air Industries, we'll call this Big Air. HEM automatically calculates long-term or chronic concentrations and risks, but acute calculations are only done if specified by the user. We will say yes here, and once you choose to do acute, you have to pick an exposure time ranging from 1 hour to 24 hours, and we will choose 1 hour. That is the default. Because short-term emissions can be significantly higher than long-term emissions, HEM has a multiplier, a default value of 10, that will scale up the annual emissions that you input to account for that when it does the acute calculations. We'll stick with the value of 10. If you have emission sources that don't vary that much, this value would be lower than 10, sometimes 1 or 2. The next question is, how specific do you want your output data to be? If you just want maximum risks, some general information, then you would say no to this question. If you want very detailed information, which includes very specific data such as the concentration from every source, every pollutant at every receptor, very detailed information. If you want that, you would say yes to this, and we will go with that. Elevations. If you have a very hilly area, or really any area that's not flat, you probably want to include elevations in your model run. So we will do that. The next choice is the dispersion environment, rural, urban. You can make this decision yourself using guidance available, but another option is to use what HEM has built in, which will look at your sources, whether they're in an urbanized area, and automatically choose that option if that is the case. Otherwise, it will run rural. So we'll go with the default. On the next screen, you specify your emission data and also what year of census data you want to use. Obviously, you probably want to use the most current data, which is 2010. If you are trying to recreate an older model run, you may want to use the 2000 census, but we will use 2010. Here you specify what your emissions file is. You can browse to find that. Typically, we put them in the inputs, and here you'll find Big Air HAP emissions file. We'll choose that. The next file is where your emissions are located and source parameter data. That is under the Big Air emission location file. This last file we not use because that is for a different source type that we don't have in Big Air Industries. On this screen, you specify optional deposition and depletion in your model run. If you say yes to this question, then you have to input more data. You have to choose whether you want to model particle and or vapor or both deposition, and if so, whether you want to do wet deposition, dry deposition, or both. If you choose this option, you do need to input more information. For example, for particle deposition, you have to put in a file that has data on particle size, particle density, mass fraction, and so on. And for vapor deposition, you have 2 additional files. We won't go into these. This is a basic demo we're doing, but these are the files you would need if you were going to do deposition. On this screen, you specify additional modeling options, including whether to include building downwash in your model run. You may need to do this if you have tall buildings or buildings that are really close to your emission sources. If you say yes to this, you need to specify this information, building heights, building widths, other information, in the form of an Excel file. For Big Air Industries, we won't do this option. The next option is whether to use the AirMod Fast All control option. This is an option included in AirMod to decrease run times by taking some algorithm shortcuts that you'd probably only want to use if you had a really large run that you wanted to do that you needed to decrease the run times. We will say no to that for our demo. The last question, do you want to create a detailed histogram of cancer risk estimates? HIM automatically gives you a histogram, but if you want a very detailed histogram, you would say yes to this. For our demo, we'll say no. The next screen defines your modeling domain. The first two values basically define the extent of your modeling domain, including the maximum radius and the minimum radius. The maximum radius allowed is 50 kilometers or 50,000 meters. For any Gaussian model, that is the maximum recommended radius. You can use anything less than 50 kilometers, and I think we'll use 20 kilometers just to make our run go faster. In most cases, you'll use 0 as your minimum radius, in which case your modeling domain will basically be a disk or a circle. If you were to choose any radius other than 0, your modeling domain would look like a donut, which is okay if that's what you choose to model. The next value is the distance within which census blocks are modeled individually. If you were to model all census blocks within 20 or 50 kilometers of a source, it would significantly slow the model run down because it's just so many. Sometimes there are thousands or tens of thousands of census blocks within these distances. And since we want to capture the maximum risk and exposure, that normally occurs very close to the sources, within several kilometers. And so the default here is 3,000, and that's what we'll use. Because sometimes census blocks are located on top of emission sources, we would not want to include those as human exposure receptors. So here we specify a distance such that if a census block is within this distance of an emission source, we will not include it as a receptor for human exposure and risk. The default for this is 30 meters, and we'll stick with that. The next two values define your polar receptor grid. This is simply the number of circles or rings and the number of radials or outward radials from your emission sources. The default values here are 13 circles and 16 rings, and we'll stick with those. HIM does allow you to input your own receptors. For example, if you wanted to model the fence line, schools, monitors, any other locations that you want to model, you can do that in HIM by specifying that in an additional input file. We'll say no to that. On this screen, you can vary your emissions. If your emissions are not constant but vary by hour of the day, day of the week, monthly, or seasonally, you can use this screen to take that into account. So if that is the case, you say yes, and then you would specify in a file exactly what your temporal situation is. We'll say no for our case. Also, if you wanted to see those detailed outputs, then you can specify that by saying yes, and then what the time frame of your outputs are, like for example 8-hour blocks, so you'd have 3 blocks per day. And also if you want to show seasonally, so you would see 4 separate sets of data for a year's time. We'll also say no to that. On this screen, you just verify your modeling options. This shows you all the choices that you've made. If you want to change one of them, you can go back. We're going to assume that we're good. We'll go on. This screen just tells you the center of your modeling domain. These are not in typical lat-long coordinates, but are in UTM coordinates. But this simply takes your emission sources, averages the latitudes, if you will, and the longitude, and makes that the center of your modeling domain. If for some reason you wanted a different center, for example, you had a lot of emission points that really weren't that significant, and you wanted to center your modeling domain on your significant sources, then you can change that with this screen. On this screen, you specify your meteorology data. As mentioned before, HIM has a built-in database of about 800 met stations, and these will be listed based on the distance from your emission sources. For example, in this case, this station is 9 kilometers away from our emission sources. You have the choice of using your own data, in which case you would have to specify the two files that AirMod needs, a surface file and a profile file, along with the date of the data and also an elevation for the location of that data. For our case, we'll go with the default, which is the nearest Met station. On this screen, your polar receptor grid is defined. The most distant ring is set based on your maximum modeling radius, which in our case was 20 kilometers or 20,000 meters. The first ring is based on your emission sources. The first ring is set such that it is beyond all of your emission sources. Between the minimum and maximum, you choose where you want your rings to be. You probably want most of your rings to be close because that's where the maximum exposure is going to be. And that's by default sets it up that way. You can see that these rings are very close together and they get more distant as you get farther out. At this point, HIM is taking your data and looking for all the census blocks that are within a certain distance of your sources. This figure is a fairly crude drawing of emission sources and receptors. You can get an idea of how far away the receptors are from your sources, like in this case it's maybe half a kilometer away. You can see a better view of this by looking at the Google Earth image, which will include your sources, nearby receptors, and you can visually see whether your sources are located accurately and whether you have, again, some census blocks that are maybe too close to your sources that you want to exclude. These are all the inputs. Our inputs are completed and AirMod is about to begin. So if you click yes here, AirMod will start running, which is what this is. This is an AirMod screen showing each day running. While this is running, we could take a look at the outputs from a previous run. Once the AirMod run is complete, all the outputs will be shown on screen, but all that data and more is available in the output directory that we created. We did a previous run of Big Air, and that data was put in this output directory. You can see that most of the output files are in the form of spreadsheet, which makes it easy to open and use and manipulate. This is the first of the HIM output screens. It shows the maximum individual risk and hazard indices. You can see that the maximum cancer risk, for example, is 2.9 times 10 to the minus 4, or 290 in a million. If you wanted specific information about that risk, for example, what source is causing it, you can click beside that and click Details by Source, and it will tell you that, for example, sample 2 drives most of the risk. It's 2.1 times 10 to the minus 4 of the risk, which is most of it. You can also see what pollutant is driving the risk. In this case, it's arsenic compounds drives most of it. Aside from cancer, there are all the hazard indices for all the different target organs, and these are the hazard indices for each one of those. The maximum you see here is 2.5. You can also see what is driving that. Again, it is sample 2, and the pollutant is also arsenic. This screen represents the maximum risk at census blocks, only populated receptors. If you wanted to know what the maximum risk or hazard index is off-site, but not necessarily at a census block, that is given in the next screen. This is all the same information with the exception of it's based on the polar grid of receptors and not the census blocks. This screen gives you population risk and cancer incidence. As you can see, for example, there are about 290,000 people at an estimated risk greater than 1 in a million. This gives you the cancer incidence. Similarly, for non-cancer, you can see the number of people who are at or above certain hazard index levels. For example, there are 5 people at a hazard index level greater than 1, and we saw that before, that the maximum value was 2.5. Other information includes cancer risk by distance. The next 2 screens provide information on acute exposures. For all the pollutants that we have emitted from big air, this gives the maximum, in our case, 1 hour concentration. That's what we specified in our input screens. It gives you the maximum 1 hour concentration, and it also gives you health reference values. You can compare to that to see whether you exceed them. For example, these values, the EAGLES, the ERPGs, these are effects levels. Other values include the California Reference Exposure Level, or REL. So you can compare your estimated concentration to those to see what level you're at. This first screen is for populated receptors. Again, those are the census blocks. And the next screen is for all receptors, including the polar receptor grid. And this is the last output screen of our run. All of these outputs from our run are also available in the Big Air Output directory that we specified earlier in our model run. Thank you for your time and interest. If you need further information on HEM, please refer to EPA's Fate, Exposure, and Risk Assessment website.